Hey everyone, welcome back, and let's write some more neat code today. Today let's solve remove nth node from the end of a list. So we're given a linked list, and all we need to do is remove the nth node from the end of the list, and then return the new list. So that's pretty straightforward, right? So in this case we got 5 nodes. We just want to remove the n equals 2, so meaning the second node from the end of the list, right? So this is the first from the end of the list, this is the second, so we remove this, and then we return this list, which now has 4 elements remaining. So what's the easiest way to solve this? Well, they say from the end of the list. That's inconvenient. If it was from the beginning of the list, it'd be super straightforward, right? N equals 2, remove this node. How can we make that even easier? I mean, what if these pointers were reversed? Can't we just reverse this linked list, start from here, and then remove the second node? And then we're done? That's definitely a possible solution, but it requires reversing the linked list, which we don't actually have to do, and I'm going to show you the easier way to do it. So let's say n equals 2 again, so we want to remove this node. So how can we identify that this is the second node from the end of the list? Like a lot of linked list questions, we can use 2 pointers. But how are we going to make use of our 2 pointers? So what if I had 2 pointers, right? A left pointer and a right pointer. The left pointer is at the beginning of the list, and the right pointer is shifted by n equals 2. So our right pointer is going to be shifted 1, and then it's going to be shifted again, and our right pointer is going to be over here. So now we're just going to keep shifting our pointers until this right pointer is at the end of the list, and watch what happens when we do that. So we're just going to be shifting each pointer by 1, and this is going to make sure that the space between these pointers is exactly equal to n, which is 2, right? So now we're going to shift by 1 again, making sure that the gap between them is still 2. Now we're going to shift 1 last time because right is almost at the end. So now our right pointer is at null, right? It's at the end of the list. It can't go any farther. And our left pointer is exactly at the node that we want to delete. And the reason is because, remember, the offset between these two is n, making sure that we have the node we want to delete. Now there's only one problem. We have access to the node that we want to delete, but we want to delete it. How do we delete it? The only thing we have to do is take this pointer, cross it out, and then reassign it over here, right? Once we've done that, we've gotten rid of this node. So the problem is we're at this node when really we want to be at this node if we want to delete this node. And this can actually be solved by another pretty common technique, the dummy node, right? So we're going to actually have another node that we insert at the beginning of this list that we don't really use. And the main thing that's going to happen is instead of our left pointer being initialized here, we're actually going to initialize it at the dummy node. So left is really going to be initialized here, and our right pointer, though, is still going to be initialized over here. So in reality, when our right pointer reaches the end of the list, we will have a left pointer at 3, and then we can update its pointer, removing this node that we want to remove. And to return the new linked list, all we have to do is take our dummy pointer and say return dummy.next, which is going to be this node. And since this is a 2-pointer technique, the time complexity is going to be big O of n. So just like in the drawing, the first thing we really want to do is create a dummy node. We don't really care what the value of this node is, but I'll just say 0. But we want to make sure that the next pointer of this node is set to the head of the list because we're inserting it at the beginning. Next, we can initialize our left pointer to dummy, and we want our right pointer to be head plus 2, right? Or head plus n, whatever n happens to be. So we need a loop to do that, right? We can't just do that with a calculation. So we can initially say right is equal to head, and while n is greater than 0 and right is not null, we want to keep shifting right. So shift right. So we can initially say right is equal to n happens to be 2. So we need a loop to do that, right? We can't just do that with a calculation. So we can initially say right is equal to head, and so shift right by 1 and decrement n by 1. Because once n equals 0, that means we've shifted by the amount that we wanted to shift by. Once n 1 and decrement n by 1. Because once n equals 0, that means we've shifted by the amount that we wanted to shift by. And the last thing we want to do is keep shifting both of our pointers now. Now we're shifting left and right, reaches the end of the list. So we can shift our left pointer and we can shift our right pointer. Now, last but not least, we actually want to delete the node, and remember, all we need to do to delete is update the left node's next pointer, and it's going to basically be shifted by 1. So left.next is going to equal left.next.next. So for example, if my left pointer was at this node, its next pointer is at 2, but I want to set its next pointer to 2's next pointer. So basically what I'm doing is this. And we know that dummy.next is at the head of our list, which is what we want to return. We want to return the updated list. So we can just return dummy.next. We don't want to include our dummy node in the output. We never wanted to add a node to the list. We just wanted to remove a node. So our solution works beautifully. We could is the end of the list. So we can shift our left pointer and we can shift our right pointer.
Mm. Babaw, mamaya. Oh, awesome. Oh, um, ah, ah.